In this video, I'd like to demonstrate a novel DCC Servo Decoder. It's novel in the sense that it has a feature which I believe no other servo decoders have, which is that the endpoints of the servo's movement can be adjusted using DCC Commands, which is to say you don't need to hook up a setting box to set the servo endpoints. I use this decoder for the semaphore signals on my Hornby 00 layout, and you may have seen one of my earlier videos where they're featured. It means I can adjust the positions of the semaphore arms to be absolutely horizontal when on and absolutely 45 degrees when off without grovelling under the baseboard. The decoder has 6 useful features which I'm listing here, and you'll need to pause in order to digest it fully. But I will discuss them all during the course of this video. The servo decoder uses 4 DCC accessory addresses. The first address is the operating address. The next 2 addresses are used to set the end stops for the servo, and the 4th address sets the direction of the servo. It's very easy to set the operational address. You simply press the button on the PCB, the LED flashes, you send the operational address that you want, and the LED flashes again in acknowledgement. Let's go on to a more detailed discussion of how DCC Commands can set the servo's end positions. Let's imagine that you set address 5 as the operating address. Then address 6 increases the angle of the servo. Now, let's imagine you've just switched on the decoder for the first time. In this case, when you operate it with address 5, it'll move a small amount to the right and a small amount to the left. What we want to do, let's say, is to set it to 30 degrees to the right and 30 degrees to the left. So here we are. We select the position we want to adjust, in this case, the right-hand side. Now I'm going to select address 6. I'm going to press the straight button, and that starts the servo moving slowly until you decide it's in the right position, and you press the turned button for address 6 or toggle it. Now, if we operate it, it'll go from a small amount to the left to 30 degrees to the right. Now we want to adjust to the left, so we set the servo to the other direction, which is here. Now we select address 6, and this time, to increase the angle, it moves to the left. So we press address 6 straight, and the servo starts to move until it gets to 30 degrees, and we press turned, and it stops there. Now if we change to address 5 and operate it, it'll go from 30 degrees to the right, 30 degrees to the left. Now, suppose you'd taken it too far. Suppose you'd pressed button 6 straight and taken it to 45 degrees. Incidentally, it stops at the end of its run. So it stops at 45 degrees, but you wanted it at 30 degrees. So this time you've got to reduce the angle of the servo, and you do that with address 7. So you press 7 straight, it starts to decrease the angle of the servo, and you press 7 turned, and it stops. So now you've got it back to 30. So it's very easy to get the precise position that you want for your end stops. Of course, these end stops are stored in the microprocessor when you've finished making your adjustments. And they're also stored, of course, during power down. Now I'm going to show you this operation with a real servo and a real DCC controller. Let's set the arm so it swings 30 degrees to the right and then 30 degrees to the left. So currently it's in the right-hand position. So if we increase the arm angle, then it moves to the right. So I select address 6 and I press the go straight button and the arm starts to move. And when I press the go turn button, the arm stops. That position is now locked into the microprocessor. Now go to the other end of the travel, which was there, and now we'll increase that travel by selecting address 6 and pressing the straight button and pressing the turn button, and now we've locked that position in. Now let's try what we've done. 30 degrees to the right and 30 degrees to the left. Now I'll demonstrate the speed adjustment potentiometer. This is the fastest servo movement with the pot set fully anti-clockwise. Now I'll set the pot clockwise and this is the slowest that the servo moves at. The built-in solid-state frog switcher is an important feature. It saves you messing around with micro switches and all the difficulties of getting them to operate correctly. Here you just take a single wire from the PCB to the frog. I'm demonstrating the frog switching by putting an LED DCC detector across the terminals. It's an LED inserted with a diode and a 1K resistor. The DCC LED detector is connected between the frog and one of the terminals J or K. If the frog is connected to K, then when we connect the DCC detector between J and the frog, it will light because the frog is connected to K and hence there's the full voltage. Now if I change the direction of the servo, now we find that the power is connected to K and F, and so that the frog is connected to J. Now I'd like to tell you something about the pulses which drive the servo. The servo has a nominal rotation of 90 degrees, and for that rotation the pulse width which we send to the servo goes from 1 millisecond to 2 milliseconds, and these pulses are repeated at a rate of 20 milliseconds. Although for this decoder with its variable speed I've altered the pulse rate to go from 5 milliseconds to 20 milliseconds. Here is what these pulses look like on the oscilloscope. The timescale of the oscilloscope is 500 microseconds per division, that is to say half a millisecond per division. So you'll see the pulse go from 2 divisions, 1 millisecond, to 4 divisions, which is 2 milliseconds. I described earlier in the video that when you first switch on the decoder, it only moves over a small range. And in this scope plot, you'll see the pulse changing from 1.45 milliseconds to 1.55 milliseconds. That is to say, a small movement about the central position of 1.5 milliseconds. This provides a convenient starting point when we're going to set the final end stops of the servo. For those who want to get more deeply into the technology, here is a sketch of the circuit diagram of the servo decoder. Notice that it's powered from a single 5-volt 1-amp regulator, and this regulator powers both the microprocessor and the servo. The microprocessor is a 12F683. The frog switches are driven from GP0 and GP1. I've drawn the frog switches as triacs because my drawing package didn't have an opto MOSFET in it. There's an interesting feature of the circuit here, quite a cunning feature, in that there's a shortage of pins. So GP4 doubles up as the input for the speed setting potentiometer and for the setting switch. The servo itself, as you will see, is driven directly from GP2.